Okay, hello everyone. Welcome to our Methods Unit 3 ATAR Notes lecture. My name is Alicia. We have a really great lecture planned out for you guys today. We're going to be going over a lot of the content that is going to be coming up in your internal and external exams, mostly related to calculus. We're going to be going over everything in like a really understandable way. I'm going to provide you guys with all the tips that I have from learning this content. And then after we've gone through the content, we're also going to go over some advice that I have for you guys as somebody who recently graduated year 12 and kind of understands the struggles and kind of can give you guys some things that will maybe help you to cruise through and really get where you want to go. So, before we get into the content, we're going to quickly go over what ATAR Notes is. So ATAR Notes provides free resources, including things like study notes, lectures, discussions, videos, newsletters, the infamous ATAR calculator. I know I use that one a lot in year 12, and articles, heaps more. ATAR Notes also provides tutoring from recent graduates such as myself, study guides with lots of content and revision materials, and then Ed Unlimited, which also has a bunch of resources. With a special thank to our sponsors. And with that over, let's get into an overview of what we're going to be doing today. So, we have a 2-hour lecture with kind of two main blocks of content. If you have any questions about anything at all throughout the duration of the lecture, there should be a box below the video where you will be able to type your question into and I will respond. If you see a question that's similar to something that you have, you can just upvote it, makes it a little bit easier. And if you're looking for any extra resources for studying, I'll also show you a few great resources to go throughout the lecture. But otherwise, if you have any questions at all, whether it's related to a question that we're doing or a concept that maybe you kind of don't understand or didn't understand when you learnt it in class, or kind of anything personal related to uni, moving out, getting into uni, applying, study tips, anything like that, pop it in the live chat and I will send you an answer. The content that we're going over today is, as I said, mostly related to calculus. So we're going to be going over, firstly, differentiation. We're going to be going over a review of differentiation and then getting into second derivatives, how to find them, what they are. Then we're going to be getting into points of inflection, and then kind of as a subsidiary of that, curve sketching and how we can use our differentiation and use our points of inflection to sketch curves and find their features. After that, we're going to be going over some optimization questions, and especially because I know that this is kind of a tricky topic for some people. It was a tricky topic for me, but kind of as a result of that, it was one of the most fun ones. I'm going to be going over some of the tips that I have for optimization questions, just because I know that they do really get tricky. And I kind of had a big list of tips for optimization. Then after that, we're going to be going over motion with relation to differentiation. So how the displacement, acceleration, and velocity all have a relationship with one another and how you can use differentiation to solve questions involving motion. And then our last topic, which is separate to all the calculus we've previously been doing, is on the sine and cosine rules. So this is just kind of an introduction to the trig that you guys are going to be going over in year 12. So we won't get too deep into it, but we will do an overview just so that you guys get the basics. After all of that, we're going to be going over my study tips that I kind of used in year 12 and a final reflection and a summary of everything that we've gone over. So, As I said, if you have any questions at all throughout the duration of the lecture, please ask them in the chat. But otherwise, let's get started. So, before we get into the content, a quick overview of myself. I graduated in 2021, so kind of, a year and a bit ago now. I got an ATAR of 99.55. And then I'm currently studying a dual degree in law and economics at UQ, and I just started my second year a few weeks ago. With that degree, I want to end up in a job related to kind of creating policy and legislation, and or creating common law, which is law created by judges. So yeah, I want to get into kind of a field related to that. But otherwise, we will get into the content now. So the first thing that we're going to be starting with is an overview of differentiation and gradient. So, as you guys might have heard in class so far and learnt in year 11, if a curve is sloping upwards, reading it from left to right, then the tangent has a positive gradient or the curve has a positive gradient. And then if our derivative at point A is greater than 0, then we say that the function f of x is increasing at that point at x equals a. So if we consider this point here that we have in this diagram, point A, the derivative at point A is going to be greater than 0, and therefore that means that the curve is increasing. So, conversely, if a curve is sloping downwards, reading it from left to right, then the tangent has a negative gradient. And so if the derivative at a point A is less than 0, then the function is said to be decreasing at that point. So, a review of all of that is if the derivative is positive, the curve is increasing. If the derivative is negative, then the curve is decreasing. And this is how we can use the derivative to know things about the curve itself. Know whether it's increasing, decreasing, what the gradient is, etc. So, the third circumstance that can happen with a curve is if it's flat. So it's not increasing, it's not decreasing, it's flat. And at that point, the tangent has a gradient of 0. That makes sense, right? Because it's kind of in between the positive and negative gradients that we were discussing before. So, if the gradient of a function at point A is equal to 0, then the function is called being stationary at that point x equals a. So in all of these scenarios down here, we have curves that have a gradient of 0 at a particular point. So here the gradient is 0, here the gradient is 0. Here we kind of have this chair-shaped function, which is what you might typically see in maybe like a cubic polynomial, I mean. We have this stationary point of inflection in these scenarios here as well. And in all of these scenarios, we have a stationary point because instantaneously, just for one tiny second, the gradient is 0 and the curve is flat. So as you can see, we kind of have two categories displayed here of stationary points. We have turning points, and then we have the points of inflection, and this is where the curve kind of has that chair shape. So now we're getting into how we can use the second derivative to know things about our original curve. And again, don't worry if some of this is kind of going over your head a little bit. We'll go over some examples in a second, which might help you understand. And again, if I'm going too fast, you can absolutely pause the recording. Yeah, so as you can see, we have our diagram here. So this curve here is the original curve, y. This curve underneath is the derivative, y dash. And this third curve here is the second derivative. So, as you can see here, and this is kind of a visual representation of what we've been going over so far. The curve here, I'll draw it in for you guys. The curve in this section has a positive gradient because it is increasing. And then also here, it has a positive gradient. But in this middle section down here, it has a negative gradient because it is decreasing. So, when we look at our derivative curve, the value of the derivative is actually positive in the two sections corresponding to the positive derivative. So in this section here, our derivative is positive, and then this section here, our derivative is positive. And then in the middle section in here, our derivative is negative because it's below the x-axis. And as you can see, these sections correspond to the original function. And this is why if our derivative is greater than 0, then we have a positive gradient or an increasing function. Because as you can see, when the derivative here is above 0, the value of the derivative is above 0, it's above the x-axis, this is when we have a positive gradient. So this is where these kind of rules come from that we were discussing before. And this is a visual representation of them if you ever need to use one. If you're maybe using the graph function of your calculator, it might be a little bit easier in a tech active exam. This is how you can tell. The other thing that I would like to point out to you guys is that we have these two stationary points here and here. So this is when the curve is kind of turning around. It has these two turning points. And corresponding to the x value of these two turning points, we have an intercept of this derivative curve with the x-axis. So remember how to find the x-intercept of a curve is when the value of the curve, or the y value of the curve, is equal to 0. So when the derivative function is equal to 0, we have a stationary point. So all of these rules that we've gone over in the previous slides have these graphical representations which really help to kind of understand where they're coming from and really help to remember them and also to apply them in graphical situations, like if you're doing, as I said before, a word question in your graphics calculator where you're kind of graphing a function or something like that. It's really easy to tell when the function is increasing, decreasing, or has a stationary point just by looking at the graph. Now, getting into the relevance to the second derivative. So, remember the second derivative is the derivative of the derivative. So the second derivative tells us about the properties of the derivative function, but it also tells us about the properties of the original function, y. So we're going to go over those now. So, as you can see here, our second derivative has a positive value here and it has a negative value here, and then it also has this x-intercept right in the center. So what we can firstly recognize is that this positive portion of the second derivative corresponds with the section of the first derivative that has a positive gradient, which is exactly the relationship that we saw between these two. But of course, because the second derivative is the derivative of this function, we can also see a similar relationship. So when the value of the second derivative is positive, it means that the gradient or the first derivative function is increasing. And then a similar thing here. So in this section where the second derivative is negative, the first derivative is decreasing. Same thing again, where the first derivative has a stationary point, the second derivative is going to have an x-intercept, and this is exactly what we saw up here. Now, the other thing that I want to point out, and this is kind of the more typical application of the second derivative, is its relationship with the original function. So, what I want to point out to you guys is that the second derivative tells us about the concavity of the original function. So, when we're talking about the concavity of the original function, we are talking about whether its gradient is increasing or decreasing. And I'm going to draw a second diagram over here. And this is of the original function, y. So, as you can see in this section here, so even though the gradient of this function is kind of what we've drawn over here, the gradient of the function and the actual concavity of the function are not the same thing. So, as I said, the concavity tells us about whether the gradient is increasing or decreasing. So, in this section here, the gradient is decreasing. So even though in this little part, in this part here, the gradient is positive, the gradient itself is decreasing. So the gradient is getting smaller and smaller. It's getting less and less positive. And this is because down here, the gradient is really steep. But as it's coming closer and closer up here, it's getting more and more flat as it approaches the stationary point. So it's really, really steep down here and getting more and more flat. It's getting closer and closer to zero. So even though the gradient itself is positive throughout this entire section, it is actually getting smaller. It's getting less and less positive. It is decreasing. And then as you can see down here, the gradient is still decreasing because it's getting steeper, but it's getting more and more negative. So even though the gradient might be -1 here, it might be like -10 here. It's getting smaller and smaller. However, at this point here, the gradient actually stops decreasing and it starts increasing. So it changes. So from here onwards, the gradient is actually getting more and more positive, and that's because even though the gradient itself is negative here, it's actually approaching zero. So it's really steep, but it's getting less and less steep, less and less steep, less and less steep, and then it gets to zero here. So it's getting closer and closer to zero. It's actually getting bigger throughout this whole section, and then as it comes up here, the gradient is positive again, and then the gradient is actually increasing again. So it's getting steeper and steeper, it's getting more and more positive. So as you can see, these two arrows tell us about the concavity of the curve, and this is the rate at which the gradient changes, not the actual gradient, whether it's positive or negative, but the rate at which it changes. So as you can see here, this section of the function has a certain concavity because the gradient is decreasing. And then in this section, the gradient is increasing, but then we have this point in here where the gradient changes from decreasing to increasing. And this is called our point of inflection. So if you have a look back over at our diagram over here, we're looking again back at our initial function related to our second derivative. Our second derivative is negative, so it's in this negative section. In the section where the gradient is decreasing, so this section in here corresponds to this section here. Then at this little dot in here, this is when the second derivative has an x-intercept. So as you can see in here, this is the point where the concavity changes, and this is when the second derivative has the x-intercept. And again, when the initial function is increasing, then our second derivative is above the x-axis. So this tells us a lot about the concavity of the curve. And I hope this visual representation really helped you guys. I know we went over that kind of in a lot of detail, so I hope that if you already understood that, it consolidated it, but if you didn't, it really helped you understand. I know it took me a little bit to get all of this stuff, all the relationships between the different curves, kind of mess you over a little bit just to begin with, but I hope this really helped you guys. If you're still having trouble with it, maybe rewatch this section of the recording. But okay, now we're going to get into the relationship between the first and second derivatives, kind of in a more structured approach. So, as I was talking about before, we have two types of concavity, when the gradient is increasing and when the gradient is decreasing. So, as you can see here, in this section, the gradient is increasing. It's becoming more and more positive. It kind of has this curved shape. And we call this concave up. And this occurs when the second derivative, this is the notation for the second derivative that we can also use as well, if you haven't seen this before. This is just another way of saying like y double dash. When the curve is greater than 0. And then we have concave down when the derivative is less than 0. So these two are kind of the most archetypal examples of concave up and concave down. So as you can see here, throughout this whole section, the gradient is increasing. It's becoming less and less negative throughout here. It's becoming 0, then it's finally getting more and more positive. And then in this section here, the gradient it's positive here, but it's getting closer and closer to 0, and now it's finally getting more and more steep and more negative. And this is concave down. An easy way to remember this, and this is how I remembered it in year 12, was that when we're talking about concave up, I just remember it as cup. That was terrible handwriting, I'm very sorry. But I remember it as cup, concave up, and as you can see, like all of the curves that we've been shown for concave up kind of have that, like, they look like they would, if you kind of rained water down on them, they would catch the water. That's kind of how I think of it. So even though this section here does kind of look like a cup, but these two sections here, like, don't really look like a cup. But if, water came down here, the two curves would capture the water, sorry. And then concave down occurs when the curve would like deflect the water. So in all of these scenarios here, the water would kind of just like rain on and then like fall off. That's how I think of it. And yeah, as you can see, these two requirements for concave down and concave up, we can also see in our graphical representation. So when the second derivative is positive, is above zero, it's going to be increasing, and that's what we saw back here. So when the second derivative is positive, then the curve has this concave up form and is increasing. And when the second derivative is negative in this section here, then it's going to be concave down, it's decreasing. Okay, this is just an overview of the notation that we use, just to refer back to if you're ever having trouble or don't understand a question. So remember, if the function is given in y, then we can differentiate this with respect to x to get dy dx. The second derivative is expressed as d squared y dx squared. And look, I'm going to be completely honest with you. I do maths at a university level, and I still don't remember where the squareds go on this second derivative. So I would recommend just kind of practicing it and do a kind of a rote learning approach, because I still do not remember it. And if our function is given in y dash and y double dash, the y double dash is the second derivative, and then similar thing applies for f of x. So pretty simple once you get used to it, but maybe something that would be helpful to pop in your notes as well. Okay, so now we're getting into why the second derivative is useful. So as I was going over before, the second derivative tells us about the concavity and the inflection points, and this kind of tells us information on how to draw our graphs, how to graph functions, like you might be asked to in an exam. Graph f of x and I'll give you a function. If you can find the concavity and the inflection points, it makes it so much easier, and tells you about the shape of the graph. We can also use the second derivative in optimization problems, which we'll get to a little bit later in the lecture. And then the second derivative also tells us about the relationship between acceleration and displacement, which we'll also get to later in our motion topic. But yes, so the second derivative is really important, gives us a lot of information about different topics. Okay, now we're getting onto some examples of finding the second derivative. So in the first example here, we have the function x to the power 7. We need to find the first derivative. So remember the first derivative, we're just going to use our power rule. We're going to take the power out the front and decrease the new power by 1. Then remember our second derivative is the derivative of the derivative. So we're now going to derive this function here. So we're going to take that old power 6 out, reduce our new power by 1. And this is going to give us 42 x to the 5th. Now, in this second question here, we're going to need to find the first and second derivative. This one is a little bit more complicated because we have our x on the denominator of a fraction. A tip, which I haven't written down these slides here, but a tip for you guys in general when you're deriving and also when you get to integration, if you haven't gotten to it already, if you are deriving or integrating a function where x is on the denominator, you need to apply your index rules to get it up to the numerator, to get it in a format that you can derive or integrate. So the index rule that I am talking about is this one, and I'll write it over on the side here. It's if you have something with a power on the denominator, you can take this up and just change the sign of the exponent. And so kind of what this means, by extension, is if you have something like, one, or 3 to the negative 2, this is equal to 1 over 3 squared. So you can just change whether the number is on the numerator or the denominator by switching the sign of its exponent. So we can apply this in our question here. So we want to take it up to the numerator, so we're going to change the sign of its exponent. So this is going to give us x to the 3. And now we can find the first and second derivative. So the first derivative, I'm going to take that power out, reduce our new power by 1. Our second derivative, we're going to derive the first derivative here. So we're going to take that old power out and reduce the new power by 1, leaving us with 6x. Okay, that was a really quick example of finding the first and second derivatives. Now we're going to get onto an application of using the second derivative to find when a curve is concave up or concave down, and also using the first derivative to determine when a curve is increasing or decreasing. So we're going to be using the rules that we went over previously in the lecture, telling us about, like the value of the first and second derivative and what that tells us about the curve. And we're also going to be needing to derive the curve. So what tells us if a curve is increasing or decreasing is, remember, the first derivative. So we're going to find the first derivative over here. So we're going to have 6x squared, take 6x, take 12. And then what tells us if a curve is concave up or concave down is the second derivative. So we're going to find the second derivative as well. And this is just going to be the derivative of our first derivative here. So we're going to have 12x minus 6. So now we're going to need to apply the rules that we learned previously. So remember, when a curve is increasing, it means that the first derivative has a value above 0, and when it's decreasing, it means the first derivative has a value below 0. Now, we can solve these using inequalities. In my opinion, it's not super necessary to learn inequalities. It still really is useful. We're not going to go over it today just because it's not super necessary, but if you are more of a high achiever, I would recommend learning it. Today we're just going to use equal signs and then kind of find the rest of the answer from there. So, we need to find when the first derivative is going to be equal to 0, and then we're going to find out, if it's increasing or decreasing on either side. So we're going to let our first derivative equal 0. As you can see, this is a pretty simple quadratic. Because it's equal to 0, we can cancel these. So we're going to get x squared, take x, take 2. So this is a pretty simple quadratic. You would be able to solve this using your ACB method or by completing the square. But I'm just going to do it on my calculator really quick because we only have 2 hours. And this is going to give us that x is equal to 2 and negative 1. So, sorry, I wrote negative 2. No, I didn't, that's an equal sign. Having a brain blank. Yeah, so our x is going to be equal to 2 and negative 1. So now what we need to determine is in between these intervals if the value of the gradient is greater than 0 or less than 0. So what I typically like to do here is use kind of a little table of values. So we are going to be finding out x in relation to the derivative. So we're going to have negative 1, 2, and then in between we're going to have other values, just any value in between these two, because this is going to tell us when the function is increasing or decreasing around those points. So we are going to sub our values into the first derivative. So we are going to have, so our derivative in this section here is going to be positive. It's going to be 0 here, negative in here, 0 again at 2, and then positive again at 3. So what this tells us is that the function is going to be increasing. Function of x is going to be increasing for the interval when x is less than negative 1 and when x is greater than 2. And then the function is going to be decreasing for the interval between negative 1 and 2. So the inequality signs that I'm using here are strict inequality signs, which means they just like less than, greater than, they don't have the equal to component as well. And that's because at the limits that we're using, negative 1 and 2, the function actually isn't increasing or decreasing. It has a gradient of 0. So that's why we're using those signs instead. So what this tells us is that the curve looks, something a little bit like this. It's going to be increasing for a certain section, then it's going to be decreasing, and then it's going to be increasing again. And this is going to occur at negative 1 and then 2. Because as you can see here, the gradient is positive up until it hits negative 1. Then it's negative between negative 1 and 2, and then it's positive again after 2. Okay, now we're going to use the second derivative to tell us about the concavity of the curve, and hopefully this kind of matches up with our visual representation of what we've got so far. So, remember a curve is going to be, we can determine if a curve is concave up or concave down based on the value of the second derivative. So, let's find when the second derivative is equal to 0. So the second derivative take 6. 6 equals 12x. X is going to be 6 divided by 12, which is going to give us 1/2. So now we need to determine what the value of the derivative is of the second derivative is, sorry, on either side of this point x is equal to a half. So we're going to use a similar table of values. So we are going to have x being equal to a half. Then we're just going to pick two values on either side. So we're going to have 1 and 0, because these are the simplest ones. So at x equals 0, our second derivative is going to be negative. It's going to be 0 to half, and then at x equals 1, the second derivative is going to be positive. So we can apply this to our graphical representation here. So in the middle, in between -1 and 2, we're going to have our point a half. And then in this section here, our second derivative is negative, which tells us the curve is concave down. And that matches up with what we've drawn here based on our first derivative. And then after a half, it's going to be concave up. So our answer as we write it is going to be that our curve is concave up when x is greater than a half, and it's going to be concave down when x is less than a half. And again, when using our strict inequality signs, because at a half, the curve isn't concave up or concave down. It isn't either one of them. So we have to use our strict inequality. Okay. Now, that was the end of that question there. So now we're going to get on to a little bit more about points of inflection. So, remember, points of inflection change us when tell us when there is a change in concavity. So it is calculated when the second derivative is equal to 0. And that's what we saw in the last example, right? We found when the second derivative was equal to 0, and then kind of at that point, that's when the point of inflection is, that's when the concavity is going to change. So, how can we, or these are, I guess, the requirements of a point of inflection. So the first requirement is that the second derivative is equal to 0, which is what we saw before. The second requirement is that the concavity around that coordinate changes. And this is really important because if the concavity around the coordinate doesn't change, then it's not a point of inflection. So, we've already gone through how to find when the second derivative is 0. The kind of real question here is, how do we check if the concavity around the coordinate changes? What we need to do is plug in the x values on either side of that coordinate, similarly to kind of what we did in the last example, and check if the sign, the positive or negative sign of the second derivative changes. So, in our last example here, the sign around the point of inflection here changed. So here it was 0, on one side it was negative, on one side it was positive. That means that it is a point of inflection because the concavity around the curve changes. However, if, for example, we'd have negative, 0, negative, it would not have been a point of inflection because on either side of that point, the concavity was concave down, which means the concavity did not change. So, this is really important. If you are asked to find a point of inflection, or if a question asks you to draw a graph including the points of inflection, which we'll get to later, you need to check both requirements, because even if you don't check the second requirement, even if you only satisfy the f double dash equals 0, you won't get the full marks because you need to check that the concavity around the coordinate changes. Okay, let's get into an example of this. So we need to find the points of inflection on the curve y equals 7x cubed plus 2x squared. So the points of inflection occur when the second derivative equals 0 and when the concavity around that point changes. So second derivative, we need to find the second derivative to tell us if the second derivative is equal to 0, obviously. So we are going to do this first up. So remember, the second derivative is the derivative of the first derivative. And our first derivative is going to be 21x squared plus 4x. Our second derivative is then going to be 42x plus 4. Okay. Now we need to find when the second derivative equals 0. So we're going to have 0 equals 42x plus 4. So we are going to be finding when negative 4 divided by 42, which is going to give us negative 2 over 21. Excuse me. So this tells us the x value of a potential point of inflection. So this was the first requirement satisfied. Now we need to check if the second requirement is satisfied. Remember, the second requirement is that the concavity around that coordinate changes. So we need to find a table of values. I'm going to have negative 2 on 21. It's going to be x. This is going to be our second derivative. Then we're going to have, just numbers on either side. So we're going to have negative 1 and 0. We're going to sub this into our second derivative to check that the values of the concavity change. So our second derivative, remember, was y double dash equals 42x take 4. So this is going to be negative. So we're going to have 42 times negative 1 take 4. And then the concavity is going to be negative here as well. Okay, so I just realized that I made a small mistake, which is that I copied this second derivative over wrong. This should be plus 4, which gives us a positive second derivative here. Okay, so this tells us that this point, negative 2 on 21, is actually a point of inflection because both of our requirements are satisfied. So our point of inflection occurs at x equals negative 2 on 21. Quick tip, sometimes questions will ask you to find the coordinate. If they ask you to find the coordinate of a point of inflection, make sure you find the corresponding y value, because just finding the x value of the point of inflection won't be enough. Another tip for that type of question, which might seem a little bit silly, is if you're finding the coordinate and you need to find the corresponding y value, do not substitute your x value into one of the derivative functions. You have to substitute it into the original function for y, which might seem very obvious, but I've done that many times, and I did really well in methods. So make sure that you're subbing your x value into the right function, being the y function, not one of the derivative functions, if you need to find the coordinate of the point of inflection. Okay, this is just a quick photo of what that curve actually looks like at kind of the interesting points. So as you can see here, our curve is kind of concave down. Then at around this negative 0.1 mark, which is the approximate value of negative 2 on 21, there's this point of inflection, and now the curve is concave up. So this is how our use of points of inflection can really help with curve sketching, because they just they tell us what the curve actually looks like and the concavity of the curve, which is really helpful. Okay, now we are getting onto the curve sketching topic. So, as you might have been able to kind of tell, we're already kind of going into a little bit, but now we're going to get into some of the other things that you need to know for finding the features of a function, the things that you're going to need to label if you're asked to sketch a curve. So, other than points of inflection, the other thing that you're most likely going to be asked to label is going to be the stationary points. Remember, the stationary points occur when the second derivative, or sorry, when the first derivative is equal to 0. So, obviously, you've probably gone over finding stationary points before. We're going to go over an example in a second. But once you've found the point when the first derivative equals 0, you need to determine the nature of the stationary point. And that means like whether it is a maximum point or a minimum point. So we have two methods for finding the nature of a stationary point. The first one is using a table of values. So this is similar to what we've been doing in the previous examples where we've been using tables of value. What you're going to be doing here is you're going to pick a x value on either side of your point where the first derivative equals 0. So here we're going to say that it's occurring at 2. And then you're going to check the value, whether it's a positive or negative, of the derivative on either side. And this is going to tell you the nature of the stationary point. So if in our example here, the first derivative is positive on this side and negative on this side, this tells us that our curve is going to look like this, because it's going to be increasing, then it's going to have our stationary point, and then it's going to be decreasing. So it tells us that our curve has a local maximum point. Now, if we switched this around, if you had kind of the opposite scenario, if we had negative and then positive, it tells us our curve is going to be decreasing, then it's going to reach 0, then it's going to be increasing. So it is a local minimum point. So that is how we can use a table of values. And what we often call this is like the first derivative test. The second option is to use what we call the second derivative test, which is where we substitute the x value that we found into the second derivative. And the reason that this works is because remember our second derivative tells us about the concavity of the curve. So if our curve, I'll draw this for you guys, if our curve is a local minimum, then it's going to be concave up, which means that our second derivative is going to be greater than 0. And if our curve is a local maximum, then it's going to be concave down, which means that our second derivative is going to be less than 0. So this is why subbing into our second derivative helps. Like, it really tells us about the concavity, but then the concavity tells us about the nature of the stationary point. So you can either remember these two rules down here, the ones here. You can remember them just kind of by remembering this process, or the way that I remember them probably isn't actually that helpful, but I just couldn't think of any other way, is that it's just kind of like the opposite of what you'd expect. You know what I mean? Like, if the second derivative is positive, then it's a local minimum. So it's kind of like the opposite, and then the same thing here. If the second derivative is negative, then it's a local maximum. And this can kind of get confusing because for all of the other rules, they kind of make sense. You know, if it's second derivative is greater than 0, then it's concave up. If the first derivative is greater than 0, then the curve is positive. All this kind of stuff, but I just kind of remember that, like, For determining the nature of a stationary point, using the second derivative test, it's the opposite. Again, that probably isn't the best way to remember it. I just couldn't really think of anything more creative. But if you guys can think of anything more creative, or if you've learned anything more creative, please feel free to tell me. I still have to remember this rule to this day, and I still sometimes get it confused. Okay, so now we are going to get onto an example of curve sketching. So in this example here, we need to find the first derivative, the second derivative. We then need to find any stationary points and determine the nature of those stationary points. And then we need to determine any inflection points. So this is kind of like a culmination of all the content that we've been doing so far in the lecture. So let's get into it. So firstly, we need to find the first derivative and second derivative. So our first derivative is going to be equal to 3x squared, take 3. Our second derivative is going to be equal to 6x. Remember, we're finding the derivative of the first derivative. And now we need to determine any stationary points and their nature. So remember, a stationary point occurs when the first derivative is equal to 0. So we're going to find when the first derivative is equal to 0. So we're going to let 0 equal 3x squared, take 3. The only unknown here that we have is x squared, so we can just solve this algebraically. We are going to have 3 equals 3x squared. X squared is going to be squared. That was the ugliest 2 I've ever seen in my life. My deepest apologies. All of my private tutoring students know just how hectic my numbers can get sometimes. So we're going to have that x squared equals 1. And remember, when you are solving an equation where you're using the square root, you always need to remember the plus or minus of square root 1, because 1 squared is equal to 1 and negative 1 squared is equal to 1. So always remember that when you're solving like quadratic equations. Okay, so this tells us when the stationary points occur, but now we need to determine the nature of the stationary points. So I'm going to use the second derivative test, just because we've been doing table of values, not specifically for this purpose, but table of values throughout the rest of the lecture. So we're going to sub these two x values into our second derivative, and this is going to tell us about the nature of the stationary points. So f double dash for 1 and f double dash for negative 1. So for 1, it's going to be positive, and for negative 1, it's going to be negative, because we just have 6 times 1 and 6 times negative 1. Now remember, if our second derivative is positive, it's concave up, which means it is a local minimum stationary point. If our second derivative is negative, which means we have a concave down curve, which means that the nature of our stationary point is a local maximum. So this tells us the nature of the stationary points and their coordinates. One more thing that we need to find is the y value of these two stationary points, just because it will help us graph and will also give the necessary information asked for in a question. Usually when you're asked a question for curve sketching, they'll ask you to draw the curve out and label any of the interesting points. Interesting points being like intercepts, stationary points, inflection points, all that kind of stuff. And you need to include both components of the coordinate, being the x and y values. So the function of 1 is going to give us 1 cubed, take 3, which is going to give us negative 2, sorry, of, write that the wrong way, of 1 is going to give us a value of negative 2, and then the function of negative 1 is going to give us negative 1 cubed, which is negative 1 plus 3, which is going to give us positive 2. So our 2 points of inflection are going to be 1, negative 2, and negative 1, 2. Now we need to determine any inflection points. So remember, the inflection points occur when the second derivative is equal to 0. And that is our first requirement. So obviously our second derivative is going to be equal to 0 when x equals 0. And now we need to fulfill the second requirement, which is that the concavity around this point changes. So again, we're going to do a table of values. So we're going to have x, we're going to have our second derivative. Our point is going to be 0, and at this point our second derivative is going to be equal to 0. Now we're just going to pick 2 values on either side, pick 1, and we're going to determine the value of the second derivative. So remember, our second derivative of x is 6x. So 6 times negative 1 is negative, 6 times positive 1 is positive. So this tells us that the concavity around our point of inflection changes, which means it is in fact a point of inflection, which is brilliant. So now we're going to get onto the last step, which is that we're going to graph it. I apologize if this is a little bit messy. So we're going to have y and x. So our point of inflection is going to occur at 0. We're going to actually need to firstly determine, or we're going to plot down the stationary points. So remember, at 1, negative 2. So we're going to have 1 down here, 1, negative 2. And then at negative 1, 2 are going to be our two stationary points. Now we know that our point of inflection is going to occur at 0, and we know that the nature of our stationary points is going to be a maximum here and a minimum here, and that's what we found in the last slide. So at 1, we're going to have a minimum, and at negative 1, we're going to have a maximum. So kind of drawing the rest of this out. This is what we get. And I apologize for the messiness. And this kind of corroborates that we have our point of inflection here at 0. So yeah, this is how we can use the stationary points and the points of inflection to graph a curve. Telling us information about the nature of the stationary points and about the concavity of the curve. The one more thing that you need to do is probably find the intercepts, which you should know how to do. But other than that, that is basically the basics of curve sketching for polynomials. So we're going to go over another example again, and this one is a little bit more difficult, but it also kind of illustrates a key point, or like a key tip that I'd recommend you guys remember for any kind of question involving calculus. We'll get into that. So firstly, we need to find the first derivative, and then we need to determine any stationary points and use a table of values to determine their nature. So what we have here for our function is we have a product, because we have x multiplied by kind of a different function, which is x take 2 cubed. So we have a product. The other thing that we have is a function to a power. So we have x take 2, which is kind of like a linear function within itself, to a power. So whenever we have a function to a power, we need to use the chain rule. So in this question here, to find the derivative, we are going to have to use the product rule and the chain rule. One more tip that I have before we actually get into deriving it is kind of when you're reading through a question, if you see like the first part like asks you to prove something or show something, and then kind of use that result in the next part of the question like we do here, it usually means that like this first part here is like a little bit difficult. And if you can't figure this out on the day of an exam, you attempt this first part, but you just can't figure out how to show that the first derivative is equal to this, it means you just need to take this result and roll over to the next question and kind of stop wasting time on this first part. The reason that people who write exams do this is because like they don't want you to lose too many marks just because you can't find the answer to the first part of the question if that first part of the question is necessary to subsequent parts. So, takeaway, if you get this kind of question where you have like something you need to prove in the first part and then use that in the second part, if you can't prove the first part, just leave it to the end of the exam and just kind of take this result and use it, and hopefully you'll get marks for the second part of the question as well. Okay, but now we're going to get into actually deriving this. So, as I said, we're going to have to use the product rule. So we're going to have u equals x and v equals x take 2 cubed. Our u dash is going to be 1. Our v dash, remember, we're going to use our chain rule here, so we're going to take this 3 out the front, leave what's in the brackets, take this old power by 1, we're going to reduce this old power, giving us 2. Now we're going to multiply by the derivative of the thing we just left by itself, the thing we just covered over, the thing we just ignored. The derivative of x take 2, the thing we just ignored, is just going to be 1. So using our product rule, we are going to have u v dash plus u dash v, which is going to give us 3x x take 2 squared plus x take 2 cubed. Now, one more thing that I'd recommend to you guys is when you're going through your exam, if you're using kind of like a simple rule, such as the product rule, make sure you either write down a formula or just write down that you use the product rule if you don't need to write down the formula. Because otherwise, if you have a look at the marking guides, especially for the QCEE externals, maybe not for your internal exams written by your teacher, but definitely for the external exams, they always allocate a mark to kind of specifying what differentiation rule you're using. So either write down the formula or write down, just say like write like product rule in words. And then you'll get the marks for that. Okay. Now we need to prove that this is equal to what we have over here. So what we have over here is kind of a factored version of this. So a tip for when you are doing like a proof question, if you need to like show a result, usually you just kind of need to like look at what you need to prove and then look at what you have currently and kind of match the elements. So the similar elements that I can see here is that here we have an x take 2 squared, which is factorized out. So I'm going to factorize out the x take 2 squared firstly. So we can factorize out x take 2 squared. And this is going to leave us in big brackets with 3x plus x take 2, because that's what we've been left over with. The other thing that I notice about what we've been asked to prove is that we have a 2 out the front and that we don't have an x out the front like we did here. So we don't want to bring an x out, but we do want to bring a 2 out. And we do also want to have a component that looks like 2x take 1. And this is kind of what we need to do in the remaining. So, this section here, we want to match up to this section here because we've already got the x take 2 squared down pat. So what I'm going to do here is just expand what we have and see where that gets us. So we're going to have 3x plus x, which is going to give us 4x take 2. So what I recognize here is that for this second part here, we can factorize out 2 and then be left with 2x take 1 because 2x take 1 is equal to 4x take 2. So we can factorize out that 2, which gives us exactly what we want. So we're going to be left with 2 outside of 2x take 1, x take 2 squared. So that is our proven result. Now, the tip that is kind of inherent to this question that I was talking about, which is really important, we are going to get to now. And this is kind of the purpose of this first step here. So now we need to find any stationary points and then use a table of values to determine the nature. So we're going to have our derivative being outside of 2x plus 1, and then we're going to have x take 2 squared. It's going to be take 1, sorry. So now we need to find any stationary points, and we need to find when this first derivative is equal to 0. So we're going to let 0 equals 2x take 1, x take 2 squared. Now, really quickly, just take 1 second to think about how we could solve this, how we could find when x is equal to 0. So, hopefully you had the chance to think about that. What we can do is we can use the null factor theorem, similarly to if we're kind of factorizing a quadratic and then finding the solutions for it. So we can use the null factor theorem. We can say that 0 is going to be equal to 2x take 1, and 0 is going to be equal to x take 2 squared. And then we can solve it from there. So this is going to give us that x is equal to 1/2, and then x is equal to 2. And that was really simple. What I want to point out to you guys is that if we had tried to do a similar thing, just by using the first derivative that we found to begin with, which was this one here, 3x x take 2 squared plus x take 2 cubed, it would have been impossible because we wouldn't have been able to use the null factor theorem, right? So the tip that I have for you guys is if you're doing anything with calculus and you need to find like a stationary point, or you need to find a point of inflection, or like even more generally, if you have an equation and you need to find when it's equal to 0, factorize it. Factorize it. Like I've done so many questions in all of year 12, like practicing all these kinds of questions in methods. At the level you guys are at, if you get a really complicated equation and it's equal to 0, the only reason or the only thing they're ever going to be able to expect you to do to solve that complicated equation is to factorize and use a null factor theorem. So this is kind of like a similar thing that we do when we are solving quadratics, which maybe you guys actually haven't thought about before. It was kind of like a realization that I had when I first started using this tip that I'm talking about, is if you have like a quadratic, x squared plus x plus 1, whatever quadratic. What we've kind of learned in like year 10 and year 11 is just like oh, we just like factorize it and then use the null factor theorem, right? And that's because like we can't solve the quadratic in its unfactored form. And that's exactly the same process that we've been going through just now. We had this derivative in its unfactored form, and then to solve it, we needed to factorize it and use the null factor theorem. So, as I said, it's kind of a widespread and very useful tip, even in like completely different areas of maths. Um, Anything that you're going to be doing later in the year, even when you're getting into statistics and stuff like that and methods, it'll still be useful to remember that. If you have an equation equal to 0, factorize, use the null factor theorem. Okay, moving on. Now we need to determine the nature of these stationary points. So we need to use a table of values as the question specified. So we're going to have x, and we're going to have our first derivative. So we're going to have x equals a half, x equals 2. Then we're just going to pick values in between these. So we're going to have 0, 1, 3. We know that at a half and 2, our first derivative is going to be equal to 0. Now we need to determine the value of the derivative at these other values, 0, 1, and 3. So, really quickly going to figure those out. Okay, so what these look like is that this one here is negative, this one here is positive, and this one here is positive. So I just did that using the table function on my graphics calculator or using Desmos. Obviously, if you're in an exam, you'll need to use a table function on your calculator. If it's a tech-free exam, then they'll probably give you something easier to work with. Excuse me. So now we need to determine the nature of the stationary point. So I'm just really quickly going to like graph out what this looks like underneath here. So we're going to have a function that has a negative gradient here. Then it's going to reach 0. Then it's going to be positive. Then it's get more and more flat. And then it's going to be positive again. So this is what our function looks like, right? We kind of have a stationary point here and a stationary point here. So, as a quick exercise, have a think about where the point of inflection would be here, or how many points of inflection there would be. Take a quick second to pause the recording to think about this. But there is actually only one point of inflection, which is right here, because this is where the concavity changes. This section here is not a point of inflection. Oh, sorry, it is a point of inflection. My mistake. This one is also a point of inflection because the concavity around that point also changes, because here it is concave down, and then here it is concave up. My mistake. So we do have 2 points of inflection here, and then at this point here we have a stationary point and a point of inflection. Okay. So the nature of our stationary points, this is going to be a local minimum. And then this here, because it is a stationary point and a point of inflection, is going to be what we call a horizontal point of inflection. So those are the nature of our two stationary points. Okay, now we have one more harder example. So we have a curve y equals ax squared plus bx plus c, passing through the point 1, 4 and negative 1, 6. and it obtains its maximum value when x equals negative a half. And we need to find a, b, and c. So, quick tip for you guys. If you want to have a think about this question before we go to the solution, again, pause the recording. But quick tip for you guys is if you are asked to find multiple values, like the coefficients of the variables in a curve, so as we have been here, a, b, and c, the coefficients, the derivative is really, really useful because as you kind of go down the derivative, the numbers are eliminated, right? So like when we find this first derivative here, we're going to eliminate c, which makes our equation simpler because now we don't have c and we do have values for the derivative. So it's really useful to kind of use the derivatives because it eliminates those values. So our first derivative is going to be 2ax plus b. Now, we're going to write down the information that we have been given and use that to find a, b, and c. So the information that we've been given is two coordinates and something about its derivative. So we know that a maximum point occurs when x is equal to negative 0.5. So we know that y dash equals 0 at x equals negative 0.5. And remember, this is a minimum. So we have one more condition, which is that the second derivative is going to be less than 0. So we also need to prove that for this information. So what I'm going to do first up is sub this information into our derivative function. So we're going to have 0 equals 2a times negative 0.5 plus b. So this is going to give us 0 equals negative a plus b, which gives us that a is equal to b. So this is really helpful information. We don't yet have a value, but what we do have is some more information that we can use using maybe some simultaneous equations. So what we also have is these two coordinates. We can sub in these x and y values to come up with two different equations in terms of a, b, and c. So subbing in 1, 4, we are going to get 4 equals a times 1 squared plus b times 1 plus c. And then subbing in negative 1, 6, we are going to get 6 equals a times negative 1 squared, which is just a. Take b, we have b times negative 1 plus c. So this is really useful. We now have 3 equations and 3 unknowns, which means we can use simultaneous equations to find a, b, and c. So we know that a and b are equal. We can sub these two in together to get 4 equals a. We're going to sub a equals b, which is going to give us a plus c. So 4 is equal to 2a plus c. Therefore, c is going to be equal to 4 minus 2a. We can sub equations 1 and 3 into this one over here. So we're going to get 6 equals a, take a plus 4, take 2a. So we're going to get 6 equals, so a take a is going to cancel. We're going to get negative 2a We're going to take that 4 over to the other side, which is going to give us that a is equal to 1. Therefore, b is also going to be equal to 1, remember, because a equals b. And then we can sub this in here to find c. So we're going to get 4, take 2 times 1, which is just 2. So these are all of the values for a, b, and c. Again, I know this was a harder example. If you didn't quite catch everything, remember to look through the recording. But yeah, the basics of this one to remember is that just if you're asked to find the coefficient of the unknowns for a curve using derivatives, you're most likely going to be needing to derive and then kind of utilize the fact that as you derive down, the values drop off. And then you're most likely going to be using simultaneous equations to find the values. The other thing that I'd recommend for these types of questions, but also kind of questions worded like this in general, any kind of worded question, is if you are given kind of information that is maybe so not in numbers. So, it's kind of easy once you're given a worded question to like write down the numbers that you're given. But if you're given information that's not in numbers, like we were here, that it obtained its maximum value, convert the worded information into numbers. So the maximum value tells us that maximum value means stationary point, means that the first derivative equals 0. And once you've kind of written all of that information down, even if initially upon reading the question you really kind of had no idea where to go with it, once you're kind of like looking at all the numbers written down, it becomes a lot easier to kind of make the connections in your mind. At least I find it a little bit easier. And I still kind of use this strategy when I'm doing my economics degree in university. So it really does work. And yeah, I think that's everything for that question. Oh, one more thing that I should mention is I did mention that the condition for this was that the second derivative was less than 0. You can go ahead and prove that the second derivative is less than 0. But another thing that you could say is because this curve is a parabola, it's only going to have one stationary point. So that means that this point that we found, is the only stationary point. As a general rule, especially when you're getting into curve sketching, a curve can only have the number of stationary points that's one less than its highest power. So, because a quadratic, the highest power is 2, so it can only have a maximum of one stationary point. Similarly, for like a cubic, because the highest power of a cubic is 3, it typically has a maximum of 2 stationary points. So a cubic can kind of look like this, but a cubic can also like look like this, and it only has one stationary point. So that's what I mean. It's cubic, the highest power is 3, it can have a maximum of 2 stationary points, but it can still have one. Okay. Yeah, that was just a general tip for curve sketching of polynomials. Okay, let's move on. So, now we are getting onto our next topic, which is optimization. So, optimization is the mathematics of finding the quote-unquote best possible way to achieve a certain goal. Kind of like the maximum this that we can have, or the minimum this, like the maximum area, the maximum volume, the minimum cost, the minimum like time used, anything like that. We're just kind of trying to like optimize something. We're just trying to find like the best possible result. So how do we solve these problems? Firstly, we need to specify a function that we need to optimize. What this often occurs in is if we're given like a worded question without a function, we kind of need to like create that function from the words that we've been given. We need to like generate our own function. And that kind of is like where the trickiest part of optimization comes in. And I'll give you guys some tips on like things you can do to help create those functions. The second part is to use the same concepts as in curve sketching, just with the function instead. So what we're going to need to do is kind of use our derivatives to find stationary points and points of inflection and stuff like that to solve these kinds of problems. So we are going to go over some examples of when you might be asked to optimize something, and then we're going to go over some actual examples of applying this. So yeah, some example questions might be like maximizing profit, what I said before, maximizing volume of a box built from a sheet of cardboard. That's a pretty typical one. And then, as I said before, many optimization questions will kind of ask you to rearrange or create an equation. So drawing a diagram is very, very useful. If there's anything about optimization, and I do think we have a slide later on providing some tips for these, but if there's anything that you take away from optimization, and like creating an equation if you're not given one, is firstly draw a diagram. Really, really important, draw a diagram. Even if you kind of think that you're a little bit above it, it's really important just to avoid making mistakes. And if you're kind of new to optimization, it's really, really helpful to look at a diagram and be able to kind of visualize how you might actually incorporate those elements. Otherwise, it's like way trickier. The other thing I'd recommend you take away is just you really need to like practice. Like you really, really need to practice because they often will give you really difficult optimization questions. Optimization is kind of one of those areas where it's really easy to create difficult questions just out of this first element of like creating equation, because you have to use so many of your problem solving skills instead of just kind of like following a procedure. So yeah, practice, really practice. And then when you're practicing, make sure you're practicing like a range of questions of different difficulties. Start with the easier questions, but then make sure you practice like harder questions. And then when you are practicing these questions, if you find that there's kind of like a strategy that really helps you, or like kind of a few interesting things that you saw on how to generate these equations, write them down, and then you can go back to them when you're studying for your internal and external, because that is just so useful to like kind of have a look back through of your, your big 50% exams and kind of think, oh, a strategy for optimization is to use like Pythagoras or something like that. But we'll go through a few more of those tips once we've gone over these examples. So here we have kind of a very basic optimization question. It's not worded, it's purely in maths, but it's still a little bit more difficult because we do need to create our equation ourselves. Now, a typical thing that you're going to see in optimization questions is you will be able to kind of express things in terms of like two equations, but both of those equations will have unknowns in them. So in our two equations that we've been given here, x and y are occurring in both of these equations. So we can't just use both of these straight up, right? Because we want to find something between p and x, but we don't want this y here. We only want a function in terms of p and x. So what you're going to often have to do is use some substitution. So, summary, optimization questions, you'll usually have like two equations or two like kind of equations that you've been able to come up with, expressed in terms of like two different variables and one thing that you want to optimize, but you want to create a relationship between the thing you want to optimize, and here it's p, and then like one of the variables. So you'll need to use substitution. So in here we know that y is going to be equal to 8 minus x. So we can sub this into here. which is going to give us p equals x squared plus 8 take x squared. Now we can simplify this a little bit, so we're going to get x squared. We're just going to use our binomial expansion, so we're going to have 8 squared. Take 2 times 8 times x plus negative x squared. And it's getting messy, but this is going to give us 2x squared plus 64 take 16x. Now we need to find dp dx. So this is the perfect equation that we have now because we can derive p with respect to x. So dp dx is going to be equal to 4x take 16. And now we need to find the value of x for which p obtains its minimum value. So remember, when we're finding a minimum or a maximum value, that's going to occur at the stationary point. So we need to find when this derivative is equal to 0. So we're going to let this equal 0. So we're going to get 16 equals 4x. X is equal to 4. Now, the question asked us to find when p obtains its minimum value. So we need to actually prove that this value is a minimum. And this is one more thing that you should be very, very, very wary of in optimization questions. So often you'll be asked to find like a minimum or maximum value. You need to determine, or you need to like verify that the point that you've achieved is a maximum or a minimum using the skills that we've learned previously in the lecture. Because otherwise you will lose marks, which seems brutal, because, we've only been, we know that there's only one stationary point on this curve, but it's asked to find the minimum value, so we do need to prove this is a minimum. You can do this in a few different ways. If you have a quadratic, you can just say, well, like we do here, a quadratic only has one stationary point, therefore this has to be a minimum. But the kind of typical way to do this, because you're most likely not going to get something as simple as a quadratic, is to use a second derivative test or to use the table of values, like we were doing before when we were determining the nature of a stationary point. So, our second derivative test is what I'm going to do. So our p double dash is going to be equal to 4. So this tells us that the concavity of the whole curve is constant and that it is always concave up, which tells us that our stationary point has to be a local minimum, which is exactly what we needed to prove. That's all we needed to write to prove that it's a minimum. Okay, now we need to calculate the minimum value of p. So all we need to do here is sub in our x value for p. So we're going to have p equals 2 times 4 squared plus 64 take 16 times 4. If you can do that in your head, I'm very happy for you. You probably could, actually, I'll show you guys how to do it in your head, just because practicing the tech-free really is an important tip, which I'll get to in the end. But what we can recognize here is that we have 2 times 16, and then 64, and then negative 16 times 4. So this is actually going to cancel out because 2 times 16 and negative 16 times 4 are actually like terms to an extent, because we have like 2 times 16 and then 16 times 4 which is the same as 16 times 2 times 2, right? Because 4 is just 2 times 2. And as you can see, like, these parts are like terms. So this leaves us with 64 minus 16 times 2. So 16 times 2 is 36. Sorry, 32. So 64 take 32 should be 32. Yeah. So that was just kind of like a simple way of manipulating the algebra to get an answer tech free instead of just kind of like having to do a big long arduous list of addition and subtraction. Okay. Perfect. So now we have one more example on optimization. This one is kind of a typical trickier question. Now, as you guys might notice, we are kind of running a little bit low on time, but I do just want to go over this one because it is so important. I want to make sure that you guys understand all the topics that we've gone through in a lot of depth, and then hopefully if we get time, we'll get to our other two topics. So here we have a 400-meter running track, which is made using two sides of a rectangle and two semicircles. And as you can see here, X is kind of like the width, not including the semicircles, and then the Y is the distance between the two parallel lines. Okay, firstly we need to show that X equals a half outside of 400 take pi Y. Now, again, this is kind of a question that we were going over before when I was saying, like, if a question asks you to like show something and then use that information in subsequent parts of the question, if you can't figure out the first part of the question, don't worry, just move on with this equation here, move on with this piece of information and get to the other ones. But we're obviously going to go through how to find this now. So the other thing that I recognize is that we have a pi in here, which probably tells us that we're going to be using something to do with the circles here. So we need a relationship between X and Y. The information that we have is that it is a 400-meter running track. So the perimeter is 400. And then we want to determine the relationship between X and Y. So just kind of at the face of it, what it looks like to me is that this Y value here is actually the diameter of this semicircle, which could be useful in coming up with our answer, right? So what we can do here is we can express this in terms of the perimeter. So we are going to have 400 equal to, and we're going to have 2x because we have these two x values here making up our perimeter. And now we're also going to have to include the circumference of these two semicircles here. So remember the circumference of a circle, given in your QCE formula sheet as well, but the circumference of a circle is 2 pi r. So we can just write this as 2 pi r, obviously, because like even though we have two semicircles, it's technically just like the circumference of one big circle because there's two of them. And now what you might notice is that we can express this r in terms of y, because y is equal to the diameter, which is equal to 2r, meaning that y on 2 is going to be equal to the radius. So we are going to have 400 equals 2x plus 2 pi times y on 2. So these two 2's are going to cancel out. And now, as you can see, we now have a relationship between x and y. We have a pi in there. This is kind of exactly what we want. We just need to rearrange it to get it into the form that they wanted us to. So they have x isolated, which means that we need to isolate x too. So I'm going to take x over to the other side, which is going to leave us with 2x equals 400. Take pi y. And then we're going to divide by 2, which is going to give us exactly the form that we have been asked to find. So this is kind of a perfect example of like where we needed to come up with an equation ourselves. And it was a little bit more difficult than our previous question because we needed to like consider the diagram and draw everything up and kind of use some more critical thinking skills. So this first part of the question where you need to come up with your own formula is kind of the trickiest part of optimization, and this is the part that I recommend you practice, because when you get to a complex unfamiliar question on optimization, they're not going to give you all of this structuring, all of these subsections of the question, because it's complex unfamiliar. They can give you these structuring questions in simple familiar, but not in the complex questions. So when you get to here, they're not going to give you anywhere near as much guidance in a complex unfamiliar question. So practice, practice, practice. Okay, so for the next part of the question, we need to show that the area inside the track will be used for other events and that its area is equal to 1/4 800y, take pi y squared. So this is a similar thing that we need to do here. So we need to find the area. So our area is going to be equal to the area of this rectangle multiplied by the area of these two semicircles. So we're going to have the area of a rectangle plus the area of a circle. So the area of our rectangle is going to be equal to xy, right? Then the area of these two circles is going to be equal to pi r squared, which is going to be pi y on 2 squared, because our radius is y on 2, remember from the last part of the question. So that means that our area, I'm just going to write this on the next slide, is going to be equal to xy plus pi on 2, pi y on 2 squared. So we're going to have our area equals xy plus pi outside of y over 2 squared. And now the format that it wants us to get us in is we have 1/4 at the front, and then we have kind of a y squared in here. The other thing that you might notice is that our y is in terms of x. So we don't actually have any x values in our area. Take a second, pause the recording to have a think about what we could do here. I'm going to go over the solution now. So what we need to actually do is we need to substitute a value in for y, right? So if you might notice from the last section, we have this lovely little formula, lovely little equation, of x in terms of y. So this is actually what we need to substitute in for x over here. So for x, we are going to have a half outside of 400 take pi y, and then we're going to have y here again, plus pi outside of y squared over 4. So this is everything we've got now. Now we just need to prove that our area is going to be equal to this form of the equation here. So we just need to rearrange it. So we need to factorize out a quarter, and then we need to like simplify everything that we've got in here. So we're going to have a half of 400 is going to give us 200. We're going to take this y, and then we're going to have a half of pi y. Again, take that y out, so we're going to have a squared there, and have pi. So as you can see, these two here are like terms, or are rather almost like terms. So we can have 200y, and then if we have a half of pi y squared plus a quarter, we have negative a half plus a quarter, we are going to get a negative quarter. So kind of what we have here is we have like a half, negative a half outside of pi y squared plus a quarter of pi y squared. So the pi y squared are like the like terms, and then we can just kind of like do our algebra to combine them together. That's what I'm talking about there. So if we have negative a half plus a quarter, we are going to have negative quarter pi y squared. And now as per the question, we need to take out a quarter. So obviously, if we're taking a quarter out of 200, what multiplies by a quarter to get 200? 800. And then we're just taking the quarter out here, so we're just going to have negative pi y squared, which is exactly what we wanted to prove. Okay, so now that we have that, what we need to do is get onto the next part of the question, which is to find the maximum area that may be enclosed. So what we're going to need to do, remember, a maximum value occurs at the stationary point. So we're going to need to find the derivative when the derivative is equal to 0, and then we need to confirm that that value is actually equal to the maximum value and it's not a minimum stationary point. So let's get into it. Firstly, let's find the derivative. I'm going to do this in this nice green color, a dash. So we're going to have a quarter out the front. Then we're going to have 800 take 2 pi y. So this is going to be our derivative. We now need to find when this is going to be equal to 0. So as you might notice here, the quarter is going to cancel out. We can just take this 2 pi y over to the other side. We're going to get that y is equal to 400 over pi. Now this tells us the y value. We now also need to determine the corresponding x value because we need to find actually, no, my mistake. We actually don't need to find, or the question hasn't asked us to find the dimensions of the running track. Typically, a question will ask you to find the dimensions, but remember, if you aren't asked to, don't do it because you're just trying to conserve time in an exam setting. Of course, if you're just practicing, it might be useful, but in exam setting, don't do anything you're not asked to. What we actually need to find is the maximum area. So we have an equation for area in terms of y, so we can just sub this in. So we're going to get area equals 1/4 800 times 400 on pi take pi outside of 400. Oh, what just happened? Side of 400 on pi squared. So now we need to simplify this. So of course, these two pi's are going to cancel out. So we're going to be left with a quarter outside of 800 times 400 on pi. And then we're going to have negative 400 squared over pi, because we're going to have pi squared down the bottom here, but then that's going to cancel with the one on top. I'm going to take this over to the next slide. So we're going to have equal to 1/4 side of 800 times 400 on pi. Take 400 squared on pi. We can cancel out these 400s because we have this quarter. So we're going to be left with 800 times 100 on pi. Take 400, and we had 400 squared, so we're going to have 400 times 100 on pi. So these are again like terms because we have the like the 800 out the front of 100 times pi and the 400. Similar thing that we were doing before. Again, this is just like a simpler way to do these tech-free instead of just kind of like simplifying it all out and then doing like a big long list of addition and subtraction. If you kind of think about it a little bit smarter, then it's usually very helpful. But we'll have 800 take 400, so we're going to be left with 400 times 100 on pi, which gives us 40,000 on pi units squared. And this is our maximum area. The one more thing that we need to do before we move on is prove that this is actually a maximum. So what we can do here is we can use the second derivative. So our second derivative is going to be, I'll just write it over here. Our second derivative is going to be negative 1/2 pi. And this is just from deriving our first derivative, of course. And because this is negative, it means that this curve is concave down constantly, which means that our point is a local maximum. So that is that question done. My advice, again, for optimization is practice as much as you can. Practice a range of questions. Draw a diagram. Remember that you need to find when the first derivative is equal to 0. These are some kind of typical ways to form equations if you're given like a complex problem where you just kind of like add some values together. Pythagoras, this is if you have something with like involving triangles. Trig ratios. Log equations as well. If you have something for like maybe population, where you need to like model the population using logs, which you probably would have gone through at the beginning of the year. Using log equations can also help. One other thing is to have a look back through the formulas on your formula sheet right at the beginning for like area and volume and perimeter and stuff like that. Those can typically help as well if you have like some kind of shape or something like that. Okay, we have actually run out of time um, to go over the rest of the content for motion and then sine and cosine rules, unfortunately. Um, I know that we wanted to go over it, but unfortunately, I just kind of went through the content in more depth so that hopefully you guys have like a more in-depth understanding of the content that we did go through, and they didn't feel like rushed or anything. Um, Before I head off, I just wanted to um, give you guys some quick reminders on just like some kind of things that you can do in preparation for your exams. Make sure you're practicing a lot of questions, maybe consistently. Just do like a small question every day or something like that. Make sure that you're practicing difficult questions. And also, something that maybe I don't see a lot in terms of advice is just to make sure that like when you're studying, it's like more of a positive experience for you. Whenever I studied maths, I always found it kind of really fun. I could just kind of listen to my music, listen to a podcast, whatever, do you know, and just kind of do some maths. And I always kind of made it a positive experience for myself. So I was never really like dreading to study maths or something like that. If you find that you're dreading it, maybe try some easier questions, maybe try some harder questions. If you feel like the questions are too hard for you and it just kind of like makes you upset to study, um, just really scale it back, go back over the basic content, and just kind of work your way up in difficulty. Don't try to challenge yourself too much. You just want to make sure that it's a positive experience so that you're more likely to study and you're, just like not dreading it. You're just going to be doing it far more often. You're going to be absorbing the information a lot more. It's just going to be a lot more of a better time. Anyway, that's it for today, guys. I hope this really helped. I hope you have a better understanding of the content. Um, I really enjoyed teaching you guys this stuff, going back over it. Um, and yeah, good luck with the rest of year 12. Go watch the rest of the 800 notes lectures if you're in physics or specialist. I'm also doing those, or I have done those lectures. You can watch the recordings for. But yeah, good luck. Don't stress too much. Um, and I really hope that it works out for you guys. And yeah, thank you so much for listening. Um, and maybe I'll see you soon.